Hi. So we're going to talk today about Reynolds numbers and centrifugation in a series of lectures. Uh, Now, something that all of you are familiar with are Newton's laws, right? And Newton's laws for motion of solids, as you can see, if I take this pencil here and throw it on my table, it continues to move. You could say that's because it's rolling. So if I throw it like this, it moves a little bit. I release it, it moves a bit, right? And depending on the geometry and the orientation, I will get different kinds of momentum, right? Now, the funny part is that for cellular life, things don't exactly work like that. And we'll see a little bit why. We'll understand the physics of it. And we'll also try to see how that affects cell behavior, basically physiology. And to me, this is very important because biophysics as such is not interesting unless it, in the sense of quantitative biology, teaches us something new about the big questions of biology. Why is something how it is? How did it evolve to be this, right? So let's get to it. Previously, we had gone over a series of topics with regard to fluids, fluid flows, concepts of viscosity, Newton's law, viscoelasticity, molecular nature of water, hydrophobic effect, and today we're going to talk about Reynolds number. Yeah. So, what happens when there is motion in water at a microscopic scale? What is the Stokes drag force? What is the effect of Reynolds number on flows? And how about life at low Reynolds numbers? So, those of you who have been fortunate to swim in the ocean or in the river or in a lake or in a well, you know that when you perform a stroke, yeah, like this young man is doing, you reach ahead, pull, and in the meantime, as your second arm is coming down again, the momentum of motion continues you for a certain amount of distance. So, in that sense, human swimming is based on momentum plus propulsion. An object in motion continues to be in motion, Newton's third law. This is also true of fish, but a little more complex. As you can see, this fish has a trout has a slender body and it turns one way, um, then turns the other way. And if you plot the long axis of the body in a plot, as in on the right hand side, then you will see that there is increasing speed and acceleration, deceleration, and a cyclical transition. And at the end, it moves ahead. And it is beautiful. I always enjoy watching fish swim because I think they're very elegant and I think there's something fascinating about how things move in fluids. Um, as you remember, F is equal to ma, motion which is basically mass into dv by dt. Change in velocity leads to force, but there's also an opposing force of friction or drag. And that's why things come to a stop eventually. So in fluids, we are most familiar with Stokes drag force, and many of you may have come across this already. For simplest objects, for calculating drag force, we assume a sphere. Why do we assume a sphere? This is a good question, and I want you to contemplate it. The short answer is simple geometry. So it has one dimension, radius, that becomes what we call the length scale, the characteristic length that defines the object. And its motion, in the case of an actively propelled motion, is driven by some force that drives motility. There is an opposite situation where the object could be static, but there is flow coming at it. The fluid is in motion, and then it experiences drag again. The first case, motion of the object itself by active motility, is like bacteria or leishmania or any motile self-propelled cell. And the passive motion, meaning to say the object is suspended in a motion of a fluid, in a fluid which is itself undergoing motion, is like red blood cells in blood. where they then follow the flow. So the Stokes drag equation is this: F is equal to 6 pi eta r v. What do these symbols mean? F is the force, that is the drag force. V is the velocity of the object or the flow. Eta is the viscosity of the fluid, dynamic viscosity. Remember, we talked about kinematic and dynamic. This is dynamic viscosity. R is the radius of the sphere, and 6 pi is just is a proportionality constant. You can actually derive this. We're not going to derive it today. Let's plug in some numbers since we mentioned bacteria swimming. What are the typical drag forces experienced? So for bacteria swimming, they could take many shapes. As you know, they can be rod shaped, they can be spherical, they can be ellipsoid, they can be curved, they can be spiral. So this diversity, we have to deal with it somehow. And in biophysics, we always try to take the path of the simplest situation. Not because we are not aware of other situations being in existence, but because otherwise we will never be able to draw on general laws, right? And that's what you want to do. So one of the simplifying assumptions is a spherical assumption. The other, almost sort of, you could argue, biological simplifying assumption is take a model organism. And one of the things we do for bacterial motility is to take Escherichia coli as a model organism. You remember in chemistry, we always talked about hydrogen atoms. What's so special about hydrogen? Well, many things are special about hydrogen, but most importantly, it's simple. If we at least understand the simple things, then we can go and try and understand the more complex things, right? So, velocity of bacteria swimming, like E. coli, is 30 micrometers per second between 10 to 30. So, let's take 30 as an outer limit. The diameter is approximately 1 micron, so the radius is 0.5 micron. This is assuming a sphere. And the viscosity is 10 to the power minus 3, 1000 Pascal second, which in the units comparable to the micron is piconewton second per micrometer square. How did we get this conversion? It's written over here. 1 Pascal second is 1 Newton per meter square into second. That is, when you go to piconewton, pico, remember, is 10 to the power minus 12. Meter is minus 6 squared is minus 12. So minus 12 cancels out. 1 Pascal second is equal to 1 piconewton second per micrometer square. That's how I got this answer. So coming back to the equation itself, F drag, the force of drag, is equal to 6 pi eta r v. So r is 10 to the power minus 3 piconewton second per micrometer square. I'm sorry, that is eta is 10 to the power minus 3 piconewton second per micrometer square. R is 0.5 micron. V is 30 micrometer per second. The answer is 0.287 piconewton. That is the force experienced by a cell. Now, if you don't know anything else, it's a little unnerving to think, what does this mean? What does 2.287 piconewton mean? Let's say rounding off 0.3 piconewton. We'll see in a minute, because everything will depend on the motile force against which this thing is acting, right? The drag force. In active motility. In the case of red blood cells, as you recall, they are the most numerous cell type. That's why our blood is red, human blood. By the way, there are animals with blue blood, and plants don't have blood. So blood is not ubiquitous, but at least in vertebrates we see, in animals, large animals with circulatory systems, we see it. Small insects have lymphoid systems, and diffusion is used to transfer oxygen. Blood is an aqueous suspension. It has many constituents. RBCs are a major cellular constituent. In humans, red blood cells, mature red blood cells, do not have nuclei. They're enucleated. When they're born, however, they have nuclei. So the chromosomal DNA. Capillaries that form the smallest terminal blood vessels have a diameter of around 2 to 5 micrometers, whereas the RBCs have a diameter of approximately 8 microns, 7 point something you will find in the textbooks. The flow velocity is 0.8 millimeters per second. So knowing all this, 0.8 millimeters per second is 800 micrometers per second. Radius is 2.5 microns. We took an average of the thickness and the diameter, and 6 pi eta r. So we get 37.7 piconewton. That's a high amount of drag. And this probably comes from the very high velocity as compared to the bacteria, as well as the larger size. So these two multiplicating effects. So think about it like this. 6 pi eta r v tells us that the drag force increases proportionately with the size of the object, and the velocity of the flow or the object that is in motion itself. If you increase the viscosity, you also get higher drag. If you decrease the viscosity, you reduce the drag. Very often, we may not have a choice about the fluid we are in. Like the submarine is moving in water, in the oceans. It doesn't go in a soup of honey. So, in some senses, some things we can treat as constant, some things we need to take care of the variables. So, what is the effect of this viscosity on motion and on flows? Turns out that Osborne Reynolds came up with such a number called Reynolds number, where he showed that these qualitatively different scenarios of a static object, sphere in a flow, will experience different kinds of streamlines of the flow. So you remember laminar flow in your high school textbooks. So it turns out at very low Reynolds numbers, you will get laminar flow, but anything higher than 1, around 10 to the power 120 over here, you will see little eddies. 100, you will see large vortices, and 10 to the power 4 and 10 to the power 6, the motion is chaotic of the fluid flow lines. So what kind of Reynolds numbers can we expect? So at a macroscopic level, fish like a labio rohu fish has an approximate velocity of 1 to 10 centimeters per second, which is 10 to the power minus 2 meters per second. Viscosity remains 10 to the power minus 3 Pascal second. So substituting the values of Reynolds number, and the equation is given here, which is Lu by gamma, by nu. Nu is nothing but kinematic viscosity, but kinematic viscosity itself can be written in terms of the terms eta by rho. So when we write it out, we get something that then looks like this: Lu rho by eta. Rho being the density of the fluid, eta being the dynamic viscosity that we've been familiar with. Now, something to bear in mind, if we substitute these numbers, we get a value. We get 10 to the power 3. This is for fish, Reynolds number for fish, labio, 1000, right? And if you recall this, 10 to the power 3 is somewhere between these turbulent phase. But what are the units? What are the units of Reynolds numbers, right? So let's try to calculate this. We substitute units for L, which is meter, for velocity, which is meters per second, all in SI units. Density is kg per meter cube. Eta is viscosity, which is Newton, Pascal second, which is Newton per meter square into second, which Newton itself is mass into acceleration, so it is kg meters per second square. So all of that put together becomes kg meters per second square in the numerator multiplied by second divided by meter square. All this, when we write it all out, comes to meter square into kg into second square upon meter cube into meter into second into kg, and all units cancel out. What does this mean? This means that Reynolds number is dimensionless and therefore also unitless. These kind of numbers, dimensionless numbers, unitless numbers, are quite interesting because they suggest that this one number, as we saw here, by just knowing this, irrespective of the physical nature of the object that we are studying, can give us an idea of what its properties might be. And this is exciting. I hope that you realize that these very elementary concepts in fluid mechanics apply very nicely to biology, and we'll see this right away. Because compared to our fish, when we take a E. coli, model bacterium, gut bacteria, well-studied, genome size 4.6 into 10 to the power 6 base pairs, that is to say 4 million base pairs, its hydrodynamics are dependent on the cell size, with a length of 2 micron, width of 1 micron, average diameter 1.5 micron, radius of 0.75 micron, and swimming speed of 10 to 30 micrometers per second. So let's substitute the numbers. Using approximations, L is approximately 1 micron, 10 to the power minus 6 meters. 30 microns per second can be approximated at 3 into 10 to the power minus 5 meters per second. Velocity can be taken as 30 microns per second, which is upper limit. We can maybe take it even smaller. Substituting the values, we get 10 to the power minus 5. Now, please note, this is minus 5. For fish, it was plus 3. Yeah, it is 1,000, and this is 100,000, 1 by 1,000, 100,000. This is a very low number, and this is therefore defined as low Reynolds number. So when we return, I'm going to talk about what happens to living systems at a cellular scale. Remember, this is cellular biophysics, when the Reynolds numbers are this low. So we've spoken so far about Reynolds numbers and how we can obtain very low Reynolds numbers in the case of cells. It took the work of Ed Purcell in 1976 in a classic paper, which is in fact the text of a speech he gave, to highlight the special properties of such low Reynolds numbers. So we're familiar, and I mentioned it earlier too, that by Newton's law of motion, those objects that are in motion will continue to be in motion. This is inertia. This is your standard experience also in our scale of the world as human beings. That is to say, if you are swimming, you make one stroke and you hold on, you wait for a bit, you will continue gliding in water. Yeah, I'm not all of us are in water all the time. We're not fish. With fish, we see this. But with single cells at low Reynolds numbers, this does not hold true. And this is the really interesting part, because there is almost no inertia, or it is insignificant. It's not that it doesn't exist, and we'll see exactly what we mean by that more precisely in a bit. Part of this can be seen from the equations themselves. So if R is equal to Lu by nu, where nu is the kinematic viscosity, then rewriting it, it becomes Lu times rho upon eta, rho being density and eta being dynamic viscosity. This is in terms of the ratio of inertial to viscous forces. And of course, the R itself is attributable to Osborne-Reynolds. He used it for flows to decide whether they're turbulent or not. But Purcell found that low Reynolds numbers indicated dominance of viscous over inertial forces. And he then went on to discuss what that means for single-celled organisms. For example, he back-calculated what happens when you take the ratio of eta squared by rho. Eta is in SI units Pascal second, which is Pascal square second square. Rho is kg per meter cube, that is density. We write Pascal in terms of Newton per meter square, that is Newton square per meter to the power 4. And we are still left with kg in the denominator. So Newton's comes from force, which is mass into acceleration. Mass is kg. Acceleration is meters per second square. Substituting that, we get something that has kg square meter square second to the power 4. We already had second square. We have meter cube kg, and we had Newton per meter square, which became power 4. And this resolves to kg meter per second square, which is nothing but newtons, and this is force. And this is thought to be, at least in concept, to be the quantification in some senses of the viscous force. In order to know the magnitude of this viscous force, we can substitute numbers. And for water, we know the values of both eta and rho. So substituting them, we end up with 10 to the power minus 9 Newton, or 1 nanonewton. which is also 10 to the power minus 4 dyne. So when R is equal to 1, the force can, a force can tow almost anything, because the opposing force is quite small. It's, as we said, nanonewtons, right? So for fish labio, R is 10 to the power 3, that is Reynolds number is 1000. For human swimmers, we have taken not a typical human, but the best human, Olympic swimming record 50 meters, freestyle 20.424 seconds, works out to 10 to the power 6, 500 to 10 to the power 6, that is 5 million is the Reynolds number. So clearly, at a macroscopic scale, we are way above R is equal to 1, and the force that matters most is the inertial force, because it is nanonewtons, the viscous force. But at small size scales, length is 20 microns, velocity is 20 microns per second, like for example, the parasite protozoan, Trypanosoma mexicana, which has a length of 20 microns, which includes its flagellar tip, the leading edge, has a Reynolds number of 10 to the power minus 4. So what about the coasting distance and time at your Reynolds number? So in order to get the coasting distance, so remember coasting distance is nothing but the distance for which once the active motion stops, how long does the object or the cell continue to propagate, right? That's what is coasting distance. For horizontal damped motion, we can then, keeping this thought in mind, that we are interested in the time after flagella stop beating, hypothetically, we can equate the drag force and the force due to motion. Force due to motion can be written as ma, which is m dv by dt, and drag force is written as c1 times v. c1 is in turn the drag constant, and v is the velocity, m is the mass. Rearranging, we get dv by dt is equal to minus c1 v by m. By definition, d e to the power x by dx is equal to e to the power x, and we can use this to solve the integrate, in some senses, the dv by dt equation 1 to arrive at v of t is equal to v naught e to the power minus c1 t by m. So this exponent is in terms of time, the drag coefficient, and the mass. At t is equal to 0, the velocity is some initial velocity, v naught. That's what we will call v naught. Further differentiation of equation 2 by dt results in d by dt of this term and the right hand side, and by doing some arithmetic and defining x is equal to minus c1 t by m, we end up with this expression. So graphically, this implies that the time scale of viscosity, velocity, is set by m by c1. Velocity goes to 0 when time goes to infinity, and displacement when time goes to infinity goes to m by v naught upon c1, which we call x max, the maximal displacement. To find the maximal distance traveled, then we only need to integrate x versus t, and we have this slightly more clunky looking expression, which is in terms of the displacement after stoppage of active motion, or for example, beating of flagella. So in order to find the coasting distance and time, we need to just substitute values and we will get the number. So you should try it yourself. For E. coli, m is equal to rho times E volume, it's approximately 10 to the power minus 15 kgs. C1 is about 1.9 into 10 to the power minus 8 kg per second. Coasting distance comes to 4 by 100 angstrom, that is 0.04 angstroms, whereas coasting time comes to 0.2 microseconds, where microsecond is 10 to the power minus 6 seconds. This is only simply telling us there is no coasting and it's for a very short time, if there is any. Another theorem, which is a not very rigorously proven one in the case of Purcell, but later on was addressed a bit more carefully, is what he refers to as the scallop theorem. Scallops are nothing but single-hinged, macroscopic, shelled organisms. They have a muscle that contracts and opens the mouth, the two shells, creating a sort of clapping motion, sort of what we would call clapping with one hand. Yeah. At low Reynolds numbers, this motion would remain stationary because of what is called reciprocity. As you go from open to closed and closed to open state, it doesn't matter whether you do one faster or the other or slower, you will, because of the lack of inertia, be at the same position. And biological solutions to that is to avoid reciprocity of motion, meaning to say that the motion one way and the motion the other way are not the same. They don't retrace the path. For example, a corkscrew or a flexible fork. Some of these are seen in sperms and flagella, and therefore we could argue that this may be a solution that biology has already arrived at. What about efficiency? How efficient is the bacterial flagellar motor? Work of moving the object versus metabolic energy spent is what we would call this efficiency. Multiply 100, we get a percentage. It's about 1%. That doesn't sound like a lot. 1% is a very small number. It's a minority. Most of the energy is dissipated. But interestingly, this small number is actually very important, because if we now consider velocity of E. coli of 30 microns per second, 1% efficiency is 2 into 10 to the power 8 ergs per second, and given the mass of E. coli is about 1 picogram, it is about 0.5 watts per kilogram. What about engineered systems? What humans have been engineers of human nature have been able to do? All the engineering graduates should be very excited. Oh, our engines are more efficient than bacterial engines. Well, turns out they're about 15 watts per kg, which is almost 30 times less efficient than bacteria. So, lastly, why bacteria swim versus their the effect of diffusion can be studied in terms of something called a time for stirring transport. This is a number that Ed Purcell came up with the idea that if you divide L by velocity, you end up with a time characteristic, which is a characteristic time, which can tell us about the transport by velocity, by active motion, and L square by D, which will tell us about the typical time scale for the transport by diffusion. And if D is the diffusion coefficient, then the diffusion time by the stirring time tells you which dominates. So if the value is greater than 1, then diffusion time is greater and stirring time is very small, or the other way around. Then if the ratio stirring number is very small, then the stirring time dominates. We need some numbers, diffusion coefficient of macromolecules. We are interested in how cells may move based on the mobility of the molecules they want to eat. So we take molecule like a sugar molecule of 10 to the power minus 5 centimeters square per second diffusion coefficient, length scale of the bacterium of about 1 micron, and velocity we know is about 30 microns per second of E. coli. So we now substitute all these numbers and we end up with 10 to the power minus 2. It's a small value. Like I said earlier, if the value is small, then it is probably not diffusion limited, or diffusion is a very small time scale. Stirring is much longer time scale. In other words, stirring does not achieve much. Yeah. So this is sort of meant to be used to help us think of the following scenario, that there are molecules of nutrient type in various parts of the environment of the bacterium, and it has to decide what to do. Should it just wait in one place? Should it be like a sort of baby and a very, very helpless student who is waiting to be spoon-fed. In this case, spoon-fed not by its mother, but by diffusion. Or should it move around, try to move its hands and legs and get somewhere and see what happens? So it turns out that bacteria need to outrun diffusion by traveling a certain distance. So what is the minimal distance is what Ed Purcell asked. And that distance can be found by simply thinking in terms of the ratio of the diffusion coefficient of the molecules to the velocity of the bacterial motion. And that gives us something in the range of 30 microns. So 30 microns is what they need to swim before they can outrun diffusion and get somewhere. And the run and tumble motion that is actually observed in E. coli, in bacteria of this particular type at least, this is about a little equal to or more than 30 microns. The regions where E. coli undergoes directed motion. After that, it diffuses around, which are called the tumbles. So in a sense, Ed Purcell's point is that bacteria have discovered the physical laws that govern their behavior and have tuned their behavior at a single cell, very simple organism level with no brain, no neurons, to do something very, very intelligent. So with that, I end this segment, and you've gone through a lot of these topics: fluid flows, concepts of viscosity, Newton's law, viscoelasticity, Reynolds number, life at low Reynolds number, and we will now start a new topic.